everyone. My name is Genderson, and working with my mentor on REU, I've performed microstructure analysis on copper silver wire samples. The high strength conductors are used in pulse magnets here at the U.S. National High Magnetic Field Laboratory, and they're manufactured from copper alloys. This research is seeking to quantify the hardness and conductivity with the requirements of the resistive portion of our 45 Tesla hybrid magnet in mind. This multi-step process includes hardness testing, heat treatment, and other processes to prepare samples for examination under high-powered microscopes, such as scanning electron and transmission electron microscopes. If you look here at figure 1, there's a tensile testing rig. In this tensile testing rig, there's a copper chromium fatigue sample, and it is mounted. And in this rig, it would be subjected to repeated physical stress, similar to the stress in a pulsed magnet. This testing is a very good way to see how long it will last when it's utilized inside the magnet, as well as the method of failure once it wears out. Figure 2 depicts some Struer's roto-polishing machines that I use to bring samples from their rough, uneven original state to a smooth, clean, polished state to view them under the Helios scanning electron microscope. Figure 3 depicts a view of a dent in a copper silver wire sample from a Wilson hardness tester. I use this machine to make a deformation on the surface of the sample, presses with a known force, and measuring the dimensions of this dimple allows me to quantify the hardness. Figure 4 depicts the view of a copper silver wire sample from under the scanning electron microscope. The grain structure of the copper is visible as black cracks across the image. It might be hard to see from home. And we care about the grain structure and size, as it is a good way to quantify the known relationships between grain size and distribution and hardness, as the smaller and more evenly spaced the silver, which is the white globs you can see on top, as the smaller and more evenly spaced the silver is throughout the copper, the greater the tensile strength and the lesser the conductivity of the sample, and vice versa. So, some different methods of sample preparation that I went through this summer. I spent a lot of time in the lab preparing samples and doing hands-on work, which I very much enjoyed. And So one of the methods of preparing samples for the transmission electron microscope involves something called dimple grinding. It's a spinning grinding wheel lowered onto an extremely thin sample, and it grinds away until there's a extremely small hole in the bottom, which is the ideal setup to view through a transmission electron microscope. Figure 5 shows a failed sample that happens as part of experimental work. Figure 6 shows a sample in process. Figure 7 shows the view of a sample through the transmission electron microscope, which is a lateral view of copper silver wire. The transmission electron microscope imagery allows for viewing of grain structure and grain size, as well as grain orientation, which is something that we're interested in. So some results in data analysis. During the fatigue testing of the wishbone samples of copper, chromium, zirconium, I collected data. These plots depict the delta E values representing the change in strain of a material during the loading cycles. Delta E is on the y-axis, and the x-axis represents the cycle number. As the sample undergoes cyclic loading, the delta E values fluctuate, indicating the magnitude of the strain change experienced during each cycle. Plots 1 through 3 depict the cycles at the beginning, middle, and end of the strain test. We capture approximately 20 strain observations per cycle, and I created Python code to identify the max and minimum strain per cycle and compute the delta strain, and plot the delta strain by cycle for the sample that was recently processed. The patterns in this sample were non-uniform, which was different from some of the other samples that we have been looking at. So the 45 Tesla hybrid magnet is the MagLab's flagship magnet, and through the process of examining properties of copper alloys that will be used in the magnet, is multi-step and intensive. The knowledge gained regarding the properties of the copper composites will aid in improving the magnet through increased conductivity and physical strength for the interior components, contributing to increased power and longevity of the magnet for the users at the MagLab. This research will directly improve the use and function of the magnets here at the MagLab. I'd like to thank my mentor, Dr. REU. I'd like to thank Dr. Han and Dr. Kwana Johnson. And I would also like to thank the MagLab for hosting the REU, as well as the National Science Foundation for the funding. Thank you, everyone.